Hi everyone, my name is Maria Zachary. I hope you guys are all doing well. Today I will be talking about how physics controls prosthetic walking. When we think of prosthetic legs, we usually picture the external device, such as the metal, the carbon fiber, or the plastic that is replacing the limb. But underneath that, there's an entire story of the forces, energy, and motion that determine whether someone is able to walk comfortably, safely, and confidently in their prosthetic. My goal in this presentation is to show that prosthetic feet are not just medical replacements, but rather they are also carefully engineered physical systems. I will walk through some of the key physics principles, such as ground reaction force, energy storage and return, stiffness, and compensation, and show you how all of these affect real people living with limb loss. Let me start with the core idea. Walking is controlled by physics, not just muscles. Every step we take is dependent on three main things. Firstly, force pushing against the ground. This is the interaction between our feet and the floor. Secondly, energy that is stored and then released, especially around the ankle joint and the tendons. So, this demonstrates the physics of potential energy and kinetic energy, which is a key physics idea. Thirdly, torque, which is the rotational effect of forces at joints such as the ankle, knee, and hip. In a biological leg, these elements cooperate automatically. The ankle flexes and extends, the Achilles tendon behaves like a spring, and the hip and knee coordinate to keep the body stable. We don't really think about it, it's just physics working in our body. However, in someone with limb loss, especially below the knee or above knee amputations, part of this system is missing. So the prosthetic device has to reproduce the missing physics. If the forces are too small, or if the energy isn't returned at the right moment, or if the torque isn't controlled, walking becomes tiring, slow, and sometimes unsafe. It's easy to think that we just need something foot shaped to stand on, but a prosthetic foot is much more than that. It's also a mechanical system that has to take over multiple jobs at once. So, firstly, it should support body weight during standing. It has to be strong enough not to deform excessively or break, even when the person is leaning, turning, or carrying objects. Secondly, it has to be able to transmit load safely to the ground. That basically means that the forces should be distributed so there aren't painful pressure points in the socket or unstable movements at the knee. Thirdly, it has to control forward motion during walking. As the person rolls over the foot, the device has to guide how quickly their center of mass moves forward. And finally, it also has to reduce stress on the knee, hip, and spine. If the foot doesn't absorb enough shock, those higher joints end up taking the impact and walking feels really tiring, which it shouldn't. When any of these tasks isn't done well, we can see decreased balance between walking and the workload of the muscles, increased fatigue, and a higher risk of overuse injuries. So, designing a prosthetic foot is really about balancing all of these mechanical demands at once rather than just being the shape of a foot. Now, I'm moving on to one of the most important concepts in walking, which is ground reaction force, which is often shortened to GRF. Whenever your foot hits the ground pushes back with an equal and opposite force. That's Newton's third law in action, which is the force of A on B equals the negative force of B on A. This force travels up through the foot, the leg, and the rest of the body. This ground reaction force does several things for us. It keeps us upright, which counteracts gravity. It moves us forward because part of the force is directed backwards on the foot, which pushes the body in the opposite direction. And it stabilizes our joints because the line of force relative to the knee and hip determines whether those joints are pushed into flexion or extension. Prosthetic feet change both the timing and the magnitude of this force. If the foot is too soft, the GRF builds up more slowly and the person may feel like they're sinking before pushing off. If it's too stiff, the force spikes quickly and can also feel jarring. Lower or poorly timed GRF means slower movement and reduced stability, which is why prosthetic alignment and choice of foot design is super critical. Another key idea is energy storage and return. In a natural leg, the Achilles tendon and surrounding muscles store energy when the ankle dorsiflexes and then release it as the ankle plantar flexes during push-off. This is a very efficient biological spring system. Some prosthetic feet try to mimic this by using carbon fiber blades or plates. These structures bend under body weight as the person progresses over the foot, store elastic potential energy in the material, and release that energy when the person pushes off into the next step. You can think of it like compressing and releasing a spring. When this process is tuned correctly, the user benefits from less muscular effort because the device helps with propulsion, smoother walking since there is more continuous transfer of energy from step to step, and better symmetry, meaning that prosthetic side and the intact side behave more similarly. Without good energy return, the body, especially the hip muscles, have to generate more power actively, which can be tiring and can also lead to long term strain of the muscles. This is where I'm going to talk about prosthetic feet, which take things a step further. So, passive feet, even advanced carbon fiber ones, have an important limitation, which is that they can only give back the energy you put into them. So they're like springs. If you don't compress them, they can't push you forward. Powered feet, which are different, use motors and actuators to actually add mechanical energy to the system. They're connected to batteries and controlled by sensors and microprocessors. These feet can actually push the body forward, especially during push off, help restore a more normal walking speed, which is closer to more able bodied individuals, reduce hip strain and compensatory movements, and decrease overall fatigue because the user doesn't have to generate all the power themselves. Research and engineering groups, like those referenced in my work cited, are exploring designs where the angle and torque are continuously adjusted based on the person's gait cycle. This moves prosthetics closer to functioning like a robotic joint rather than passive support. Now I want to zoom out and look at walking as more of the whole. One of my favorite ways to describe gait is to say that walking is a repeated controlled forward fall. So, with every step, your center of mass moves ahead of your base of support, which means you literally begin to fall forward. Your foot strikes the ground and then catches that fall. Okay? And then the leg and foot push you forward into the next step, and then the cycle continues. In someone using a prosthetic, the device has to provide enough support and control to manage this sort of controlled fall. If the prosthetic foot is too unstable at the heel strike, the person feels like they might collapse. And if it doesn't smoothly roll over, they may hesitate or more shorten their steps, which isn't really an efficient way of walking. So, poor control of the process leads to knee buckling, where the knee suddenly gives way, and to fear of falling, which is a major reason many amputees limit their activity. So, again, the mechanical design of the prosthetic directly affects the person's confidence and mobility. Another design engineers and prosthetists work on is stiffness. So, stiffness determines how much the prosthetic foot resists bending when weight is put onto it. It controls both the shock absorption and energy transfer. So, if the foot is too stiff, it doesn't compress enough, very little shock is absorbed, and more of the impact travels straight up to the knee. And over time, that can contribute to joint pain and degenerative changes. However, on the other side, if the foot is too soft, it collapses too much under load. Energy that could have been returned as forward push is lost as heat in the materials, and the person can feel like they're walking in deep sand, which is really tiring and inefficient for the purpose of walking. So there is an optimal sweet spot where stiffness provides safe loading, which means comfortable impact and efficient propulsion. This optimal stiffness isn't the same for every person. It depends on numerous factors such as body weight, typical walking speed, terrain, and activity level. Properly matching stiffness to the patient is a key part of prosthetic prescription. Up to this point, I've really focused mainly on the prosthetic side, but the rest of the body has to react to whatever the prosthetic is doing, and that's where the idea of compensation comes in. So, when the prosthetic cannot generate enough power, or if it doesn't roll over smoothly, the body automatically tries to make up the difference. Common compensations can include the hip muscles working harder on the prosthetic side to swing the leg through or lift it higher, the intact leg absorbing more force because the person subconsciously trusts that side more and spends more time on it. Back and core muscles increasing their work to stabilize the trunk during uneven or jerky steps. And these compensations might help the person get through the day, but they do have serious consequences that take effect more on the long term. Over months and years, they lead to joint degeneration, especially in the intact knee and hip, chronic pain in the lower back or shoulders, and very asymmetric gait patterns, which can limit speed and endurance. So, a prosthetic that doesn't handle the physics well doesn't just affect the limb, but it also affects the whole body's mechanics. To wrap up, the main message I want to leave you with is that prosthetic walking is a physics problem first and a medical problem second. Walking depends on how forces are transmitted from the ground to the body and how efficiently energy is stored and returned and how torque is controlled at the joints. Prosthetic feet don't just replace the missing tissue of a limb, they replace the physical functions that limb used to perform. When biomechanics are optimized, stiffness is well tuned, and energy return or powered assistance is matched to the person, the result is less pain, less fatigue, better balance, and most importantly, more independence and quality of life for people living with limb loss. Here is my works cited. These are the links to where I got all my images for the slides. And also, I watched Autobook Academy and I watched a recorded webinar on how prosthetics function. So that is where I got my information for this slideshow. Again, thank you so much for listening. I really appreciate your time and dedication in watching my video. Thank you so much, and I hope you guys have a great day.